My name is Rob Davis, and I am from NVIDIA, and along with my co-presenter, Curtis Ballard from Hewlett-Packard Enterprise, we're going to be talking about a new capability of NVMe over fabrics that allows you to boot OS image across the network. So let's get started here. So here's our agenda. We've broken it up into like the organization, the high-level architecture, all the pieces, and that I'll cover along with some background from NVMe.org. And then Curtis is going to go into the nitty-gritty details. So here we go. So for those of you that do not know what NVMe Express is, or NVMe.org, it's an organization that was started, a long time ago, over 100 members, and it was put together to create a standard for connecting SSDs to processors. In the beginning, you guys might remember there was the SSDs were connected with legacy hardware, hard drive interfaces like SAS and SATA, and they were, hard drives we think of as slow now. They weren't then, but those interfaces, put constraints on the SSDs, and so there were some startups. I think Fusion.io, Violin at the time, that started connecting SSDs to PCIe, and NVMe.org was put together to standardize that effort. And it was very successful. As you guys all know, NVMe is ubiquitous in most of as the storage or the connection to SSDs across the industry today. So the standard is broken up into 5 different pieces, and I'll go into more details on those in the next slide. But it's been so successful, this standard, that different applications in the lower left, different parts of the IT industry have been able to take advantage of that performance that it's provided for connecting SSDs. So the standard is on version 2.0. Here are the 5 different pieces. You guys can try to guess or look at the pointer as to the part this talk is about. The base specification, the command sets, which is kind of the API, that's where basically what you'd think of as a standard sits. And then there's the transport specifications, which comes into play here with what we're going to talk about, because unique to NVMe, most standards like Fiber Channel, for example, is designed around fiber channel wires, SAS around SAS wires, InfiniBand around InfiniBand wires. But NVMe can support all kinds of wires. In fact, it supports 2 different Ethernet wires, RDMA and TCP. And it supports InfiniBand, and it supports NVMe. So it has different transports for those different wires that it runs over. And then there's the management part of the specification that applies to all the different groups. And then there's a new one that we put together to do the boot specification. And our first standard was released, or the first version of the standard was released less than a year ago in November. So the work gets done in NVMe.org in 2 different organizations, the marketing working group and the technical working group. The marketing working group is the one that put this talk together, and the technical working group is where the specifications actually get done. And we had to form a new, what's called task group. The different task groups focus on different parts of the standard, and we had to form a new one for boot, and that has 34 companies in it. NVIDIA and Intel and Dell hold the chairmanships for it. And if there's anybody out there that wants to join it, feel free. If you're in NVMe.org, which is easy to join as well, we can use all the help we can get it with future parts of the standard that we're working on, and Curtis will go into some of those. So why in the world did we want to put all the effort it took to get this standard out? And the reason is because for those of you that aren't familiar, boot over the network is a little bit different than what you do with your laptop, right? In your laptop, there's an SSD in it, or maybe a hard drive. And when it's turned on, the BIOS goes and finds the boot image and loads it to the CPU, and you're up and running. The difference in over a network is that you've got a network in between, so it gets a lot more complicated. And that's what this standard's all about. And why it's important is because in order for a large data center to operate efficiently, you really need this capability, because think about like an OS upgrade or patches, going to thousands or tens of thousands of servers and loading the new operating system. Very inefficient, very time consuming. Whereas with boot across the network, you just put it on the boot, the storage system that has the boot image on it, you put the new one on or the patches on and reboot all the machines across the network and you're up and running. So very important capability and needed to make NVMe over fabrics, take all this new performance that came out of NVMe SSDs now across the network in fully capable technology. So we chose for version 1 of the boot specification to use the transport for NVMe over TCP. And the reason was because it would allow us to develop it faster by leveraging iSCSI boot across the network. And what we were really interested in leveraging was their architecture, which I'll show you in the next slide, their high-level architecture, but also the table that's called the IBFT, which is a handoff of certain parameters needed between the boot part, like the small operating system that does the booting, to the main operating system image that comes across. And you have to hand off some images like where the storage systems are, a whole lot of things Curtis can go into details on. That was something we wanted to leverage, and I'll show you why in a couple slides here. And then we also wanted to leverage the basic flow and handover architecture mechanism. And you can see that we were pretty successful in that. And there's a couple of obvious changes, right? In SCSI, which is the language of iSCSI, you have LUNs, and in NVMe you have namespaces. So obvious things like that, subsystems, but the overall high-level architecture we were able to leverage. And this really helped our development, the speed of our development of the spec. And you remember that one piece of information on the IBTF, or the IBTF. Well, we invented our own version called the NVMe boot firmware table, or NBTF, and that dropped right into the architecture. And so here's what the standard looks like from a high level. Like the management part of the standard, which kind of overlays the other three parts, the boot does as well. So it isn't like we rewrote any of the basic commands or components of the standard. We just leveraged them to create the boot standard. So we're kind of a sit on the side, like, and as the middle standards go forward and new features are added, the boot will work with them. Our standard is broken into two pieces, the normative and the informative. This is similar across NVMe.org specs. And think of normative like the actual, digital details, right? What X does, what its function is, that sort of thing, what values go in there. And then the informative is like explains why, why is X important and where does it fit in the overall standard. So this is a very complex effort, involved many different pieces, and here are the four main parts. So I mentioned earlier that there's other standards organizations that were involved. So the UEFI, which is an industry standard which controls the basics of how you boot. There's the DMTF, which handles the basics of management. There's Redfish, which is a management protocol, I guess, for want of a better word. There was the NVMe.org, which we're all part of. And then there was what the name of this talk is, Timberland, which was a SIG developed to do open source and open source reference example of the boot specification. And I'll go into details on these and where the different parts fit. So that MBTF, you can see, had to be incorporated into a part of the UEFI specification or standard called ACPI, or the ACPI spec. And so that was one component. And then also the device path had to go into the boot software piece of our architecture. And here shows a lot more detail, and I'm not going to go through all this, but these slides will be put out onto the website of the Flash Memory Summit, so you can look through it in more detail then. And there's also URLs in the bottom to the actual specifications. And then for DMTF, we wanted to take Redfish to use our secrets registry. So when you go across the network, you have to know how to get through the security of the device that has the boot image on it on the other side of the network. So we wanted to leverage the management interfaces of Redfish, which are incorporated into the DMTF standard. And here's kind of a snapshot of that. And again, I don't know if there's a URL on this one. It might have fallen off. But anyway, you can go out to DMTF and look at details there if you want to. Or you can download our open source code that I'll get to in a minute and look at it that way as well. So then we put all that together in our standard in the boot standard task group. And this is a high-level image of that. And you can see all the details there. Again, won't go through it all in the interest of time because I need to give Curtis some time here. And then finally, to do the open source code, NVMe.org, you might remember when NVMe Fabrics, for example, came out, they had organization that did open source code for reference architectures. And that kind of went away in all the wars with China and China trying to theoretically steal our technology. So we had to form a separate organization, and that's called Timberland. And the companies that did it are listed here. And that organization was put together just to take the specification that came from NVMe.org and implement it in a reference architecture. And the URL down at the bottom is where you can go and download that and give it a try. And with that, I'm going to turn it over to Curtis.
Thanks, Rob. Now I get to talk about all the fun stuff here. So the Timberland SIG that Rob mentioned wrote a bunch of reference code to implement the NVMe over Fabrics boot specification from NVM Express. And, as technologists are, we're really excited about all we implemented here and want to share it with you in great detail. So I've got probably more slides than I can get through, but we'll try to fly through this, and feel free to grill us later. So to help understand a little bit about what we had to do for NVMe over Fabrics boot, we thought we'd start with a little bit of a quick overview of the UEFI boot process and the 7 stages of the UEF boot process that are implemented in the Tiana Core EDK2 reference implementation that's widely used for UEFI boot systems. The different levels of the boot system, we start out with the security level that does basic platform security, and for this implementation we didn't have to touch that. So then you move into the pre-EFI or the PEFI phase, and this is where all the configuration information is collected about the system. It collects the things like the NQN of the target system, the IP address, the target port number, and a lot of this information in some of our reference implementations, we developed some tools and manually entered information in from shell scripts. We got a little bit of information about that in here later. And in the most recent builds, we've started putting in some graphical tools so that this will look just like systems that you're familiar with when you have to manually point your system to a specific location to boot. That loads up information that then transmits into the driver execution environment, or the Dixie phase. And this is where I think all the cool fun stuff is done. Most of our code that was implemented in this space, in the Dixie phase. The system has to read the configuration in variables that were loaded in UEFI earlier. And then here is where it actually sets up your network, the interfaces, the routings, makes your connection out to the NVMe storage device that was specified in the previous phase. It can optionally retrieve authentication credentials, and it can perform NVMe over Fabric discovery and authentication. and then it connects to the NVMe subsystems that are providing the namespaces that are potential boot sources, stores all that information in the NVFT, which is later made available to the OS as an ACPI table. The optional steps there were the discovery pieces. There's some reference code in there for the discovery pieces. The authentication pieces are still a future implementation. After the Dixie step, then you have to go into the boot device selection phase. If you've spent much time messing with computers over the years, you've probably seen this lots of times. We had to modify the boot device selection phase a little bit, but it still looks like something that you're probably familiar with. This is the part of the boot process where the boot manager menu provides a list of the different storage devices out there, and sometimes it will tell you about whether it's found an operating system at those different storage devices, and you can select which one you want to boot from. In this example here, we've got a UEFI has found a NVMe-Fabric boot device with a Linux operating system on it, and if you look at the device path section there, you can see that your nice, succinct, pretty NVMe-Fabric device path is listed there. Once you've selected which image you want to boot from, then we go into a phase that's called the transient system load, the TSL phase. So the transient system load phase is called transient because at this point it's set up so that it can hand off execution to other tools, such as a bootloader like Grub if you're booting Linux environments, and it takes all of the configurations that were established in the previous step and makes them available into things like a Grub bootloader, but it's persisting the UEFI connections at this point. You have all of the connections that UEFI established are all set up, and the bootloaders can access those exact paths. So now you've got the NVFT. The table's all been generated, it's put into main memory, and it's available there for the operating system to access when the operating system boots. Moving on, we get to the runtime phase. At least we hope we get to the runtime phase because this is where all your real work happens. So at the runtime phase, the NVFT is in the system memory. So the operating system can read the configuration from the NVFT. It can set up the network interfaces and routing. Now, this is at the operating system setting up its own network interfaces at this point. It can, again, optionally retrieve authentication credentials, perform discovery and authentication, connect to the NVMe subsystems, and then provide the namespaces to other parts of the OS. You might notice that this is a lot like what was done in the Dixie phase. In the Dixie phase, the UEFI bootloader had to understand all the NVMe devices and create connections and start transferring information back and forth as a block device. At this point, we've had to transition over to the actual operating system running, where the operating system can see the NVFT in the system memory, and it's totally in control at that point. It can use administratively configured information, or it can take the NVFT, or it can take a combination of those two so that it can create the connections back to the storage devices that you started booting off of. And it's kind of interesting when you come to the OS handover and initialization. I wanted to point out that one of the things that we did a bunch of work on is to help with the second case we've got on the slide here. In the normal operating system boot, we've got the quote-unquote simple case where the system comes up. It connects to the NVMe-Fabric subsystems. It attaches namespaces. It discovers an operating system on the namespace and starts loading that namespace and booting from it. I think we all know that case pretty well. One of the areas that took a lot of work in this process that was a little bit trickier is operating system installation case. in the operating system installation case, the earlier steps, the driver execution environment phase, Dixie phase, comes up and scans the different namespaces out there, and it is going to find some namespaces that don't have a bootable OS. If you're in a brand new system deployment, it may find a whole bunch of namespaces, none of which have a bootable operating system on them. So it has to keep that information in the NBFT and have it available so that if you have a OS installation image, the OS installation image can do the initial boot up process, and then when it's up to the point that it can access the NBFT, it can look into the NBFT, find the available namespaces that don't have a OS image at this point. Well, actually, you can find all the namespaces. They may have an OS image, and you can write your new OS image into one of those namespaces, either updating an OS image or writing a new OS image to it. So the operating system installation case is quite a little bit different here, and that's fully implemented and functioning in the reference code that we've got today. So the reference implementation of booting over NVMe TCP that the Timberland SIG created, as Rob said, we had to create a special group that wrote this source code. It was very much a cooperative effort. A lot of different people from different companies put this together, created the pre-OS time boot code that's the EDK2 NVMe over Fabrics UEF driver for the TCP transport today. Started with the TCP transport as the one that's got the most interest and most widely deployed. And so the ACPI NBFTs produced by the UEFI implementation example code that we have prior to the OS boot. And then there's work that had to be done in the OS boot and the runtime. So the team has also worked on a Linux reference implementation that will expose the NBFT information to the user space, and it will consume the NBFT information to reattach to the namespaces and boot from them. And then it enables common command line tools like Draycut, NVMe, CLI, et cetera. You may be aware of to use that. So moving right along, this slide here, you may wonder why we're even showing this EDK2 concept architecture to the EDK reference implementation. What we really wanted to point out in this slide was that when we first started this work, there was a plan that we were going to leverage the SPDK software to create a NVMe TCP stack. During implementation, the team was actually able to create a shim layer that doesn't just leverage SPDK, but uses SPDK. So the exact same NVMe stack that is implemented in SDDK is used in the UEFI reference implementation that the team's worked on here. And all those modules in brown around it are providing UEFI support functions, building on the mechanisms already in UEFI. We had to create some pre-boot environment configuration tools that if you want to get down in deep and play around, you can use these. The NVMe-oF CLI tool works in the EFI shell, and we copied the NVMe CLI from Linux look and feel as much as possible. So there's a couple of examples here where you can do a list in a connect command that looks a lot like you would do higher up in the Linux stack. Then we get, if you want to actually run it into an operating system, there you have to have the handoff into the OS. So the work the team did in this level here, there's 3 different levels. You've got the EFI firmware, you've got the platform, you got the kernel, and you got the user space. And the blue pieces in this diagram here is existing code. We barely had to touch the EFI firmware or the Linux kernel. Almost everything that we implemented was up in user space. The EFI firmware has to be aware of the NBFT. It makes that NBFT available to the Linux OS, which exposes it through sysfs. And then there are Linux tools up in user space that can consume that information from sysfs using the tools that that you're already familiar with. We did implement 2 new subcommands in NVMe CLI to work with this. We've got a couple of examples. There's an NVMe show BFT and an NVMe connect NBFT. Those have been upstreamed and they got tweaked slightly in the upstream process, but work very much the same way. It's now NVMe NBFT show and NVMe NBFT connect. Here's an example of the new NVMe CLI command. I don't have time to talk through this. This is the free-form user-readable text format. It allows you to see the NBFT and all the information in it. One of the things that I point out here is it actually even provides a way that you can load NBFT information manually from user-defined NBFT. So you can play around with providing different NBFT information to your OS using this command. Here, it's also provides its output in a JSON format. I'd love to go through that in detail with you, but don't have time today. So see me out in the hall and we can dig into this. So the reference implementations, here's where things get really fun. There are reference implementations out there, 2 reference implementations today that are proof of concepts for NVMe boot. They're all built around QEMU in the standard KDE environment. They are available for both OpenSUSE Leap and for Fedora 37 and should work on those versions or any newer versions. And the 2 have very different bring-up sequences. So we want to show you a couple examples so you can see how the bring-up sequences are different and how they're handled differently if you want to expand this to other operating systems. There are very few prerequisites. This has made it super easy for you. You have to have your Intel-based host platform. You have to have a connection to the internet and a root privileged account to execute QEMU. The scripts will configure and install everything, and it's all set up so you can have a single test platform that you have a QEMU emulated host with the NVMe over Fabric's boot functionality in it, and you've got a NVMe target all running on a single system talking to each other. There are some future enhancements that we're planning on working on. We are planning to implement support for authentication and the use of TLS for secure channels. Working on implementing the DMTF Redfish secrets that Rob mentioned earlier, and there's plans for additional OS and installer support. There's also some planned future enhancements for the NVMe boot specification. We do want to look at booting over additional transports. We think we've set things up so that it'd be easy to add new transports. We want to get into the space where we can do management of large quantities of namespaces in large fleets, totally automated with things like management software applications talking to BMCs. And is there any plan for integration with the centralized discovery controller? So their basic discovery controller information capability is in there today, and this can read information either from a local discovery controller or a centralized discovery controller if you provide the information for where the discovery controller is. So it's capable of operating in fairly large environments as it is today and discovering large amounts of namespaces. There's some more work that can be done to make that better tied into system management tools like BMCs. It's all set up so that you can add new transport support to the boot specification very quickly and simply. We've got an example of that. We don't need to cover that here today, but we're prepared to add new transports. And here's our references and our repositories. The NVM Express for the boot specification, UEFI and the ACPI specifications, and the open source software repo. One thing we did want to point out is that almost everything at this point has been upstreamed, and so you can use the latest upstream software, SPDK, NVMe CLI. If you've got the latest upstream version, you've got everything you need for this. There's one piece we're still working on. The EDK2 code is really, really close to going into upstream staging. Hope to have it done by the conference. Got a couple of tweaks yet to do. So for EDK2, the version on the Timberland SIG site is still the one you want to use if you're testing with this or developing on it.